Hello everybody! Today we'll be creating an air handling unit for a food factory using SAM Mollier. So let's get to it. Okay, I went ahead and opened up Grasshopper and these are our inputs. So the outside supply air is 32 degrees with relative humidity of 44. So like a typical summer in a European country. And we want to cool down the food factory, remember our case study, to 28 degrees with a relative humidity of 39. Now we have also the flow rate and room gains given, but we'll get to these two things a bit later. So let's start with these 2 points. Well, we still have to define them as points in SAM Mollier. And how can we do that? We simply double click, we write dot, create Mollier point. And perfect, voila. So in SAM Mollier, we will always have this beginning, SAM Mollier dot, and then the component name. Therefore, to just easily find components, it is very nice to just type in dot and then the component name, which in this case is create Mollier point. We need two anyways, so that's perfect. Now, the inputs are the dry bulb temperature and the relative humidity, which are exactly the inputs that we are also given. But if this wouldn't be the case, we can simply also zoom in and have input the humidity ratio or wet bulb temperature, right? We need two values at least, but let's hide them since our inputs match the default inputs. We simply connect them over here and perfect. But when I click on these two components, nothing is appearing in Rhino. Where are our points on the psychrometric or Mollier diagram? Well, to do that, we first have to create the diagram in SAM Mollier. So access the component SAM Mollier dot create diagram. And if I just pop it on into Grasshopper, already I have this beautiful Mollier chart, right? In all its glory. Now let me get in on the top view. And actually it's also calibrated to Rhino. What I mean is that this line is like the line of 0 degrees. And then we know that this represents 10, right, in Rhino, and this 5. So this is the dry bulb temperature line of 10 degrees, and this is a 5. Now I think the wireframe view is a bit distracting because of all the grids and stuff, so I would prefer to go over to Arctic. I think it's a bit cleaner. Okay, so we have the chart. Oh, let me also go through the things over here. Here we can simply define the interval we want to see of the chart for the temperature, the dry bulb temperature, and the humidity ratio. And here we also can decide on the chart type. So with the help of a Boolean toggle, if it is true, then it is the Mollier chart, and if it is false, then it is the psychrometric chart. Let me show you how this works. I mean, it's not that hard, but just proof of concept that we really have the psychrometric chart. And here you go. So this psychrometric chart, and this is the Mollier diagram. I will stick to the Mollier diagram in this video. I hope that's fine. And let's keep on going. Okay, so I have the diagram, I have the points, but how do I connect these together? Well, with the help of the component SAM Mollier dot geometry, not create, this time it's just geometry. So here, SAM Mollier geometry. And the first input are the Mollier geometry lines, which are basically the lines that you want to see in your Mollier diagram. So for instance, you could choose the relative humidity lines or the dry bulb temperature lines and enthalpy lines, since I think the enthalpy lines are very necessary in the Mollier and psychrometric chart. Here we have the chart type, so we simply take the one that we decide on in this component, so that we only have one Boolean toggle. And then here are the Mollier objects, and this is where we connect our points. So boom and boom. And in Rhino, we can see these 2 points. This is our starting point, and these are our ideal food factory conditions. Okay, have I forgotten anything? I do not think so. So we can keep on going. So as I have already mentioned at the beginning, outside it's summer in Europe, 32 degrees, and we want to get to 28. So what do we have to do? Well, if the temperature inside is supposed to be cooler than outside, we need to create a cooling process. So let's go ahead with that. Dot create cooling process. Oops, sorry, getting a bit distracted over here. So we have a lot of different methods that we can use. All roads lead to Rome, that's the saying, right? And let's see what we have here. So create cooling process by enthalpy difference, by dry bulb temperature, by medium, by temperature difference, and by medium and dry bulb temperature. I think we'll just stick to dry bulb temperature in this case. I think that will work very nicely with our example. And then let's look at the input. So the start, well, the start is the outside supply air, right? That's our starting point. And now to what dry bulb temperature do we want to cool down? Well, intuitively, we look at our room conditions and it's 28, right? 28 degrees. So let's go ahead and do that. So 28, and then we connect that over here. Let me just clean it up a bit here. Okay, perfect. And now we do not see our cooling process because we still need to connect it to our SAM Mollier.geometry component. Let me also drag that already here. And here we go. That's our cooling process. But wait, that's not what we were going for, right? Because the cooling process, well, it just cools down, right? The only difference it does is it decreases the temperature. And if we think back to how the Mollier chart is defined, the temperature is along these horizontal lines over here. So it's just moving down vertically the whole time. But our outside supply air and room air conditions differ also in the relative humidity. So it isn't enough to simply cool down to 28 degrees. We actually have to cool down a lot more. So let's go ahead. So now we move along vertically down, 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 down until we reach the saturation line over here. And when we reach that saturation line, the water starts condensing. And if it starts condensing, that means that the humidity ratio decreases. So now if I keep on moving, you see that it's getting a bit skewed, right? And our goal is to get right underneath this point over here so that later we can simply create a heating process and just by changing the temperature again, rise up vertically over to this point again. I think this is not quite perfectly underneath. I think I'll just decrease it like one more. I think that's fine. So now that we're right underneath the point, now we just want to change the temperature to vertically rise up again, right? So I say SAM Mollier dot create heating process. Heating process. We have three options this time also, and it's by enthalpy difference, by temperature difference, or by dry bulb temperature. Let's go ahead with dry bulb temperature, you know, just keeping it nice and easy. So the starting point of our heating process is the end point of our cooling process, right? We want to start heating from here and go up. So let's connect that. And now, to what temperature do we want to heat up to? Well, we want to get to this point, so this temperature. So what was it again? 28 degrees. So I type in 28 degrees and connect that here. Then I take the heating process and connect it to SAM Mollier.geometry. Oops, I think I need to cool down like one more. One more degree. Yes, now it's perfect. Okay, so what did we do? We started from the outside supply air of 32 degrees and 44 relative humidity, and we got to our ideal room conditions with the help of a cooling process and a heating process. But let's take a step back. At the beginning, I mentioned that we're doing a case study of a food factory. And what happens in a food factory? Well, different food making processes, and different workers are working there, and different machines are running, and different stuff is happening. And all these different processes are influencing the surrounding air. So if you think of a pot with boiling water, if you think of a pot that is filled with boiling water, that water is evaporating and also influencing the surrounding air. increasing the moisture content, right? Or if you work for a long time on a laptop, it also starts heating up and minimally influencing your surrounding air temperature. So we need to take these things into account, and these are given by the room gains. The sensible load is the difference in temperature, and the latent load is the difference in moisture. Okay, so let's take them ahead, and I think we can drag them back over here. So what we need to do is to create a room process. So SAM Mollier dot create room process, this component over here. And the start of our room process is the end of our heating process, right? So we connect that over here. What is the air mass flow? We have only the flow rate. What do? We simply take the component dot mass flow rate. And there we connect our volumetric flow rate and can connect the mass flow rate to the air mass flow. Perfect. And then we simply connect our sensible load and our latent load. And now to see our room process, we just connect it back to SAM Mollier.geometry. And wow! So see, since we're working with such a humongous food factory, all these different processes add up. And if we hadn't considered them, we wouldn't have been anywhere near to reaching these ideal food factory conditions. So we actually need to adjust what we did at the beginning. We do not need to heat up that much anymore, right? This is the point we're at now, so we need to go a bit more down. So let's see how much down we need to go. 20 almost. I think 18 should be fine, right? We're at the same height, so that looks good. But it isn't enough. Since these room processes also influence the moisture content, we also need to cool down a bit more in order to reach this perfect relative humidity. So let's go back to the cooling process, and we no longer need to cool down to 13, but rather to, let's see, oops, going too far. I think 10 will be the sweet spot. Yes. Okay. So let's take a step back and look again at what we did. We were given the outside supply air of 32 degrees with a relative humidity of 44%. And we wanted to get to the room conditions of 28 degrees and 39 relative humidity. At the beginning, we created a cooling process, and we moved down in the cooling process vertically until we reach the saturation line. And then we take the skewed path. After we had the cooling process and got right underneath our point here, we needed to heat it up a bit. So we heated it up until 18 degrees. And then we took into consideration the other parameters we were given, the room gains and the flow rate, to see how much we have to heat up in order to get to this end point over here. So what at the beginning seemed like an easy problem with only a 4-degree difference and like 5% relative humidity difference was actually a bit more complicated than we thought. But I hope you could follow every step. I hope you had a bit of fun, and yeah, see you next time. Bye!